Good evening.
Good evening.
Welcome to the live session of Physical and Electrochemical Characterizations in Chemical Engineering NPTEL course. This is live session number 7. My name is Devarun Banerjee. I'm a PhD PMRF scholar from Indian Institute of Technology, Delhi. So in this week, basically the XRF, EDX, XPS, this kind of techniques were discussed. So X-ray photoelectron spectroscopy. So it works based on the photoelectric effect. Photoemission as an analytical tool is used basically, where X-ray photon is uh, given is incident, which knocks off an electron, and then to take that place to cover that energy loss, an electron from an uh, outer shell goes into that core region, and to uh, maintain this difference in energy, there is a additional X-ray is emitted. So an inertial electron is struck by X-ray photon. Particle energy is so high that the electron is knocked off its initial location inside the atom. The free electron leaves behind an ionized atom. The atom then regains its initial state after replenishing the vacancy at the inner shell by an electron from the outer shell, as I told. This difference in energy between the electrons in inner and outer shell generate the characteristic X-rays or X-ray photon, or characteristic free electron, which are called Auger electrons. All are emitted from the atom. K, L, and M series in accordance with the electron vacant shells being filled. K series specifies the emitted characteristic X-rays as electron in the outer shell occupies a vacancy in the K shell. Electron transfer from L1 to the K shell is not possible, and delta J would be 0, violating the second selection rule. Potential transfer from L shell to K shell would be L3 to K, L2 to K. This can be potential transfer. So L1 to K is not possible, but can be L2 to K transfer or L3 to K transfer. These are possible. The fluorescent yield is an important parameter. Fluorescent yield is used to determine an X-ray generation's relative effectiveness. For atomic number less than 4, the fluorescent yield will be 0, or for atomic number less than 8, the yield will be less than 0.5%. Okay, so in that way, with the increase of the atomic number, the fluorescent yield increases. However, it also series, L series, or M series. So XRF or X-ray fluorescence spectrometry, it assesses the chemical elements through detection of characteristic X-rays emanated following radiation from primary X-rays with high energy. Analysis is done either from wavelength or energy. Wavelength means this will be WDS, energy based will be DS. WDS utilizes a single crystal diffraction for the detection of characteristic wavelengths emanated from the sample. A single crystal has the ability to diffract a particular wavelength at a particular angle between the crystallographic plane and the incident X-ray beam. EDS utilizes a detector for the separation of the characteristic X-ray photons in accordance with the corresponding energies. Higher resolution and larger window of elemental analysis in comparison to EDS. This is the difference between WDS and EDS. WDS has a more complicated instrumentation, and the resolve relative changes in wavelength between 0.002 to 0. Energy window is between 0.01 to 0.1 kilo electron volt and one order magnitude superior to EDS. This is basic instrumentation is shown here. And the WDS spectra. Characteristic X-ray lines are dispersed in a range of the wavelength of the X-rays. Energy dispersive spectra (EDS). It is introduced as characteristic X-ray line intensity over the range of energies of the X-rays. The spectra is in the window of zero point 0.1 to 10 to 20 kiloelectron volt, and it shows heavy and light elements lines. Heavy is for L or M lines, light element lines are K lines. So EDS and WDS spectra are similar, but distinguishing individual elements is easier through EDS spectra. The characteristic line produced by a particular element manifests a distinct X-ray energy. Signal to noise ratio resolution in regards to energy is low by 10. Characteristic X-ray line intensity ranges between zero point 0.1 to 10 to 20 kiloelectron volt. The first question is the fluorescent yield will be zero for which of the following elements? Magnesium, carbon, titanium, lithium. Correct answer would be lithium. So lithium has a low atomic number less than 4. So its fluorescent yield would be 0. Lithium detector of radix instrument is cooled by water, CO2, liquid nitrogen, none of these. The correct answer is liquid nitrogen. So basically, there are two types of sensor used for DDS: HDD and silicon lithium. The traditional silicon crystals drifted with lithium, the so-called silicon lithium, were first commercialized in the late 1960s. The silicon lithium requires very low operating temperature, about 90 Kelvin, to separate charge signals and is normally cooled using a reservoir of liquid nitrogen. Okay. Apart from that, there is another detector called the silicon drift detector, or SDD. Nowadays, SDD is actually the newest technique. It has completely replaced the silicon lithium technology due to superior performance. It is much faster, has better resolution, and only requires cooling to a few tens of degrees below zero. The other lecture contains application of XRF and X-ray spectroscopy. So it compares the integrated peak intensity ratios among the elements present in the sample, and then by this kind of formula, by calculating the weight fraction of an element, calculate its percentage. Then there is primary absorption, secondary fluorescence, and the atomic number effect is the difference in the production of characteristic X-rays because of changes in atomic numbers in the matrix. This occurs due to electron backscattering and electron retardation. Electron backscattering is the fraction of the primary electrons which are scattered back without generating X-rays. And electron retardation is the continuous loss of electron energy when electrons traverse on account of inelastic scattering. So XPS, the basic principle of XPS, which is already discussed. So there is a photon which is incident and it knocks off an electron which is called a photoelectron. Then to cover this void space, an electron from a higher energy state goes to this particular lower energy. So to make up this difference in energy, rays emitted. Okay. So the see an insulate electron and photon is there. It knocks off an electron, which is a scattered primary electron, and so this will be the first step. And to make the difference between that higher energy shell electron which goes to the lower energy shell, there is a okay. So based on the what is the incident ray energy, we get the binding energy. Binding energy equals to the h nu minus kinetic energy. If you see from outside shell, basically the kinetic energy highest, binding energy low, the highest binding energy and lowest kinetic energy. Energy associated with X-rays are in the window of few hundreds to few thousand electron volts. These are called the core atomic electrons, XPS, where the core atomic states are in solids. X-rays of specific energy are incident on a specimen and the electrons are ejected with kinetic energy from the electronic states. Again, the same formula is shown. Binding energy is also the h nu minus kinetic energy. So the Auger electron spectroscopy, there is basically two steps. An example is shown. An L electron drops to accommodate core level vacancy. Okay, so basically when a photon is incident, it knocks off an electron from the core to make up this vacancy in core electron space, and L electron, which is a valence electron, it comes down and drops to accommodate the core level vacancy. Right. A KLL Auger electron is emitted for the conservation of energy discharge during step 1. Same similar kind of thing. So when in the XPS, to make up the difference, there is an X-ray is emitted or a photon is emitted and an electron is emitted. So based on these transitions, the first one transition is happening from the K, and K, this particular electron is going off, so it's K. Then to make up the K electron vacancy, the one electron from L shell, and then an electron from L is going off. So again L. So it's named as KLL, Auger electron. Okay, that thing is only written here. Okay, the number of Auger electrons ejected from a sample is much lower as compared to the scattered primary and secondary. Other than quantitative analysis, direct mode spectrum is not favored. XPS spectra plotted as the photoelectron intensity against the binding energy. Photoemission is based on core electron levels, valence levels, and X-ray excited Auger emission. Photoelectrons ejected by PDF subshells are identified by a unique fraction number such as copper 2p 3 by 2. So 1 by 2 and 3 by 2 for P, 3 by 2 and 5 by 2 for D, 5 by 2 and 7 by 2 for F, refer to the quantum number of total angular momentum of an individual electron of a shell. So these are some examples of typical carbon one or some organic sample. And the question is the continuous loss of electron energy when electrons traverse in a sample on account of inelastic scattering is called the atomic number effect. Electron backscattering, atomic number effect, electron retardation, none of these. Correct answer is electron. So electron retardation is the continuous loss of electron energy when electrons traverse in a sample on account of inelastic scattering. In the mode that introduces the distribution of intensity in a span of kinetic energies of the electrons is called direct mode, differential mode, constant analyzer energy mode. Correct answer is direct mode. Basically, these are two examples of direct mode and indirect mode. Is differential mode is shown here. So here in this case, mm, the distribution introduces an intensity in a span of kinetic energies of the electron is called a direct mode. 285 electron volt correspond to which of the following compounds? Amine, amide, urea, hydrocarbon. Correct answer is hydrocarbon. You can see 285 electron volt. It is the binding energy of hydrocarbon. Okay. Amine, amine is about 280. Amide is 288.2 and urea is 289. Typical carbon 1s binding energies of organic samples. The energy of a typical characteristic X-ray in XPS is dash compared to the energy of that in XRD, equal to, greater than, lesser than, uncorrelated to. So the correct answer is lesser than. The energy of a typical characteristic X-ray in XPS is lesser than the energy of that in XRD. Okay, which of the following is a function of photon energy? Photoelectron line energy, Auger electron line energy, both photoelectron and Auger electron, none of these. Photoelectron line energy, a function of photon energy, and Auger electron line energy is independent of photon energy. So on this figure below, you have to choose the correct K line. Uh, for electron transitions from L or M shells to the K shell. The correct answer will be L3 to K transition. You see here, and there is the L3 line. So that is basically from L3. This is the L3. So this is the L3 to K transition. Is correct. There is no L1 to K transition, neither M1 to K transition. The final question of today: what is the best technique for obtaining the composition map of a EDS, XPS, AES? None of these. The correct answer is XPS. So XPS is the best technique for obtaining composition map of a thin film oxide. So as nobody has joined this class, class. The recording will be available in the link shared with you. Thank you.